All right, so let's take a look at this problem here. We've got a cart, one of the typical aluminum carts that we've got. It's going to ram into a force sensor, and on the other end of the track is a motion sensor, and it gets these two graphs. So just looking at the graphs first, you always want to look at the graphs first and make sure you understand what they're saying. The last thing you want to do is misread a graph and then do the whole problem wrong and then go back to find you just thought it was time when it was distance or something like that. It changes things a whole lot. So take a look first. The velocity of the cart is 2.2 or something when it starts with here. It's going to accelerate until it reaches a new velocity, and that new velocity is going to be, say, 0.18 or something like that. So this is typical what we think. The cart's going to go forwards away from the motion sensor, so it's got positive velocity. It's going to hit the sensor and bounce backwards. So it accelerates while it hits it and then bounces backwards, moving in a negative velocity towards the motion sensor. The force sensor picks up force over time. So it's going along, it doesn't have any force, and the collision starts whenever it first experiences a force. So why would it just be a little bit of force and then steep and then maybe a little bit of force as it bounces off? Any ideas? Why wouldn't it be just one big kick instead of those little kick and then a big kick? I don't know exactly what the situation was, but maybe there was some compression on the front of the cart or compression of the force sensor. Maybe it bounced a little bit as it went through. I don't know. It doesn't really make too much of a difference. But it experiences a force over a time. And when you get to the test, you got to look at that and say force and time, impulse, momentum. You look at a velocity time, you think velocity, acceleration, displacements, things you can figure out like that. So once you got the graphs analyzed, start taking a look at the question. What's the acceleration? How do you solve for acceleration? Change in velocity over time. You know velocities, here to here. It's tempting to do F equals ma because forces go with accelerations hand in hand like that. But mass is the problem. You don't know it. But it asks for it later in the problem, so you're going to find it later. Don't do this because you can't. The only other way to solve for acceleration is kinematics, which leads you to this equation. Change in velocity, it goes from 0.22 to negative 0.18. To make you guess it. Just to make you guess it. And there's a certain level of knowledge that is understood that you'll have coming into physics, that you can read a graph and estimate based on graphs. And that's just what it is. I mean, I guess they're making sure that you don't think that that's 0.3 or 0.28. I mean, somebody put 0.28. I'm guessing on the rubric said it's got to be within a certain range of 0.22. The time it takes for the collision to happen. Point 0.04 seconds. And what'd you solve for the acceleration? Negative 10 meters per second squared. And it should be negative because the acceleration is in the opposite direction of which way the car was initially going. Change in momentum. First thing that I thought of when I see change in momentum is this. But again, no mass yet, so we can't go that way. So what's the only other way to solve for change in momentum? Ft more area under the curve. This requires a little bit of geometry. I add up all the little pieces. It'd be easier if they gave you a function. 6. Just to be sure, I would say, 0.5 plus 4.5 or whatever they are. Just indicate in some way that you're adding together those pieces if that's how you're doing it. Because if you say added them wrong and you put 5.5 with no work, you get nothing. But if you put the addition, there may be a point for indicating that. Or, even better, just write it. Area under the curve. That tells the person grading your exam that that's what you're doing. So if there's partial credit, you'll get it. Mass of the cart. Can you use F equals ma now that you know the acceleration? No. The problem is the force is changing, constantly changing. So unless you knew the acceleration at a single point and you knew the force at a single point, then you can't use F equals ma. You can't say, well, I guess you could do average force and average acceleration, but it's complicated. Better is change in momentum. What is delta P? What is the change in momentum? 6. Change in velocity, 0.4 from part 1. So the mass is 6 divided by 0.4, 15. No, 15. Wow, I'm putting a decimal in there. It just seems like a really large mass to me. 15 kilogram cart? It's not 6. Is it 0.6? Oh, yeah, these times are tiny. Is it 60? What is the impulse? You got 0.7? Anybody else get an impulse? 0.6? I just wrote it down wrong, I guess. It's a lot better. 0.6. So there you get the mass of the cart, 1.5. So there's just a lot of different ways you can do these impulse problems. Forces and times, or change in momentums, or kinematics. How did you solve for the energy loss? One half mv squared minus 1/2 mv squared. The only type of energy that this thing has is kinetic energy. So the change in energy is simply the difference between the final kinetic and the initial kinetic. You might say energy loss, that's work. Is there a way to figure out the distance? Area under the velocity curve from there to there? Yeah, probably do it that way. I don't know how you're going to find the area, though, given that's a weirdo shape. I suppose that that's a pretty good estimate of the area. because you'll lose a little bit here, but you'll gain a little bit there. It's 0.0. From here? Why would you do it from velocity 0 into the curve? Because this is the force, and the force is being applied for that entire area, not just the 0 point. Oh, I don't know. I mean, obviously that's not the good way to go here. This is way better. Way better. Now, the argument is, can you actually do it this way? I don't know. We can calculate this and then do it that way and see if it works out. This is way better. Did anybody do that? Anybody figure out an answer? It's a little bit. Okay. You guys can do the math. But just look at your final initial velocity as read from here and use the mass from the previous part. Here's what it is. That'd be interesting.